class, this is Econ 510, Managerial Economics class. Today is February 8th, Tuesday. The class will cover the second half of Chapter 4 of your textbook. So topics of today's discussion include understanding indifference curves, to locating consumers' optimal combination of goods, 3. Understanding the effect of price change for deriving the demand curve. Let's watch the individual video clips.
What would you do if you had Chris's preferences and $12 worth of income? How would you allocate your limited income over all the possibilities available to you? Would you buy more toys, more snacks, a lot of one or the other, or a balanced combination? How do economists figure out what consumers are going to do given their preferences and given the constraints of income and price? We're going to put the indifference curves that represent preferences together with the budget constraint, which represents opportunities, to show you how economists think about consumer optimization. Consumer optimization is the behavior of households trying to maximize satisfaction subject to the constraints of income and prices. So let's take a look now at the graph that we've developed. First, we have this dark line, which you'll recall represents the budget constraint. That is, it represents all the combinations of toys and snacks that the consumer can buy given the limited income and the price of the two goods. My axes aren't labeled here, so it doesn't look like I have a meaningful graph. Someone's going to have to give me a label. Let's see. There's a snack, so we'll label the vertical axis with snacks. And here's a toy, so we'll label the horizontal axis with toys. Make sure that your axes are always labeled, otherwise your graphs are meaningless. Now, here we have the representation of the consumer's feasibility set. That is, the opportunities that the consumer has given income and prices. So if you spend all of your income on snacks at a price of $1 per snack and an income of $12, you can buy 12 snacks. If you spend all of your income on toys at a price of $3 per toy, you can buy 4 toys. And the slope of this budget constraint represents the relative price of toys and snacks, which is the price of toys at $3 a piece divided by the price of snacks at $1 a piece for a number of 3. 3 is the relative price of toys and snacks, and it's the slope of this green line. Well, I guess it's a blue line. It's the slope of this line. Notice one more thing. This line is downward sloping, which means that its number is negative. The true slope of this line is the negative of the relative prices, but let's ignore the negative sign for just a minute and focus on the intuition. How do you think about relative prices? How do you think about the slope of the budget constraint? This number 3 says this: if you will give up one toy, if you give up one toy, you're going to have enough extra income to buy 3 snacks. 3 is the relative price of toys measured in terms of snacks. Now, if this blue line represents your possibilities, what are you going to do? Well, economists imagine that consumers do one and only one thing. That is, they seek the combination of goods that maximizes satisfaction. Let's find that combination. Look at all of these red indifference curves that I've drawn in here for Chris. All of these red indifference curves represent combinations of goods and services that are equally desirable. Here's a low level of satisfaction. This level of satisfaction on this indifference curve to the northeast represents an improvement. And you can do even better by going way, way up here to the far northeast. The further to the northeast you go, the better off you are, because more is better in this model. Now I could go in and label these indifference curves. It looks like I've labeled this one U0. This represents our baseline level of satisfaction. And an improvement, we might call it U1, which means this curve represents more satisfaction. And I might label this curve underneath here, I might call it U-1, because it's worse. See, the numbers don't really matter as long as the numbers increase as satisfaction increases. Which point is going to be the most satisfying to Chris? The answer is simple. Chris is going to choose that point on his budget constraint that lies on the highest attainable indifference curve. Chris is going to find that point that gets him to the highest level of satisfaction, and that is the point that he will choose. In this picture, the highest indifference curve that Chris can reach is the one that I've labeled U0. And the combination of toys and snacks that maximizes Chris's satisfaction is going to be 2, 4, 6 snacks and 2 toys. With 6 snacks and 2 toys, how much money is Chris spending? Well, let's see. 6 times $1 apiece is $6 on snacks. And 2 toys times $3 apiece is $6 on toys. 6 and 6 makes a total of 12. And that, of course, is Chris's income, which is why this point is on the budget constraint. The total spending is equal to $12, the amount of money Chris has to spend. So, to find the point that gives Chris the most satisfaction, find the budget constraint, and then look for the indifference curve, the highest indifference curve that budget constraint touches. Now, there's something to notice about how to identify that highest attainable indifference curve. Notice that the budget constraint is tangent to that indifference curve. That is, the budget constraint touches it in one and only one place. Any other budget constraint, any other indifference curve, well, let me make sure I say this clearly. Any other indifference curve that touches this budget constraint will touch it in 2 places. Only at this highest attainable indifference curve do we have a single point of tangency. Let's look at some other possibilities. Suppose we look at this lower indifference curve. Notice this lower indifference curve touches Chris's budget constraint up here, and it touches it again down here. The thing to notice about these 2 points of intersection is that at both of these points, the indifference curve has a slope that's different from the slope of the budget constraint. That is, it's not a tangency, it's an intersection. It's a point where the budget constraint and the indifference curves have different slopes. The indifference curve cuts into and goes through the budget constraint. Here's a little bit of intuition to let you know why this can't be the best point for Chris. Think about this. At every point on the budget constraint, the slope is 3. That means Chris always has the opportunity to trade 1 toy for 3 snacks. Down here, at this particular point, the slope of the indifference curve is flatter. That is, the marginal rate of substitution is less than 3. That is, Chris would be willing to give up a toy for less than 3 snacks, maybe just for 2 snacks. Think about what that means. Chris is willing to give up a toy for only 2 snacks, but the market will give him 3 snacks. What's Chris going to do? Obviously, he's going to trade with the market. Obviously, he's going to give up his 1 toy and take his 3 snacks. 2 snacks would make him indifferent. 3 makes him better off. That's an improvement on his situation. So Chris starts moving up his budget constraint, trading toys for snacks until he finally gets to the point at which his desire to trade is equal to his ability to trade. That is, at this point, where the slope of the indifference curve, the marginal rate of substitution, is also 3, Chris is willing to trade 1 toy for 3 snacks, and that's exactly what the market will allow. At that point, Chris can no longer improve his situation by trading away his toys. He stops. He has reached an optimum. Look at this point up here. At this point, the marginal rate of substitution is very high, higher than 3. That is, that Chris would be willing to give up more than 3 snacks to get an extra toy. Aha, but the market will only charge him 3 snacks. He's willing to give up 4. So what's he going to do? He'll give up the 3 snacks and take an extra toy, and he's better off. He's better off because he was willing to give up 4 snacks, but he only had to give up 3. That is, he pockets an extra snack as he moves down the budget constraint. Chris makes himself better off. He continues to trade until finally the marginal rate of substitution is equal to the relative prices in the market. So there you have it. The condition for consumer optimum, the condition for maximizing satisfaction, is that the marginal rate of substitution is equal to the relative prices of the goods in the market. At that point, an indifference curve is tangent to the budget constraint. And that's the highest level of satisfaction that Chris can afford. Let's do a quick summary here. The budget constraint represents your opportunities, and its slope is the relative price in the market. The indifference curves represent your preference, and their slope is the rate at which you will trade off the goods, one for the other. The consumer gets the most satisfaction by finding the highest attainable indifference curve. That's going to occur at the point where the budget constraint is tangent to or touches the indifference curve at one place. The interesting thing about that point is that's the place where the relative prices are equal to the marginal rate of substitution, the slope of the indifference curve. That's the point at which the rate at which the consumer is willing to trade is equal to the rate at which the market will allow him to trade. Now, let's mess with that budget constraint and see how the optimum point moves around as prices change. This will get us a demand curve. We're back with our indifference curves and our budget constraint, and we're getting ready to derive the consumer's demand curve. Remember what we did last time. We showed that if you have a set of opportunities created by your income and prices, and a set of preferences, you're going to look for the most satisfaction you can get, given your constraint. That point of maximum satisfaction will be where your budget constraint touches the highest attainable indifference curve. Now, what's going to happen if your opportunities change? How will your behavior change if the constraint changes? In particular, how will Chris behave if we reduce the price of toys? Let's cut the price of toys in half, from $3 a piece to $1.50 each. What would Chris do in those circumstances? First, let's show in our graph the new budget constraint. With the price of $1.50 each for toys, the vertical intercept remains unchanged. We haven't done anything to the price of snacks or to Chris's income, so if he spends all of his income on snacks, he can still afford 12 snacks. However, if he spends all of his income on toys now, at a price of $1.50 per toy, he can afford to buy 8 toys instead of 4 like before. So here is Chris's new budget constraint. Our blue line here represents his opportunities with an income of $12 and a price of toys of $1.50 each. What's Chris going to do? As usual, he's going to look for the combination of toys and snacks that gives him the most satisfaction subject to this budget constraint. And that means looking for the highest attainable indifference curve. Well, it's clear that the highest attainable indifference curve in this picture is the one that's labeled U1. And the combination right here, 2, 4, 6 snacks and 2, 4 toys, that is 4 toys and 6 snacks, this particular combination represents Chris's optimal choice. Let's make sure that point's attainable. Of course, it's on the budget constraint, so we know that it is. 4 toys times $1.50 each gives us a total of $8, and 4 snacks at $1 apiece gives us a total of $4. 4 plus 8 is 12. Once again, Chris satisfies his budget constraint. How do I know that this particular combination is the best Chris can do? Because it represents a point of tangency between an indifference curve and the budget constraint. This is the point at which Chris's marginal rate of substitution, that is his willingness to trade toys for snacks, is equal to the relative price of toys and snacks. That is what the market will permit. You always find the optimal point where the indifference curve is tangent to the budget constraint. That's always the best that he can do. So, even though there are other indifference curves that are way up here to the northeast, Chris can't reach them because he doesn't have enough money. Even though there are other indifference curves that are below, they're irrelevant because they intersect the budget constraint. They're lower. Chris can get to a high level of satisfaction, the highest he can attain, by finding the point where the indifference curve touches the budget constraint at only one point. U1 is the highest level of satisfaction he can get. Notice what I did here. I changed the price of toys, and I looked at how Chris's optimal choice changed. He buys more toys than before. Before he was only buying 2. Now that the price of toys has fallen, Chris buys 4 toys. What I'm getting to is a demand curve. When the price changes, the quantity demanded responds, and that's what a demand curve is. In the next lecture, we will put the indifference curve budget constraint diagram that we have here before us, we'll put it on top of another axis and use this apparatus to derive a demand curve. What we're going to be seeing is the foundation for the demand curve, that is, where it comes from using this more basic theory. We've put indifference curves and budget constraints together to find the consumer's optimal choice under the constraint of the budget and prices. Last time, we showed how when the prices change, the consumer's optimal choice changes. Now we're ready to use the tool we've developed to show where the demand curve comes from. Where does a demand curve come from? It comes from consumers making optimal choices subject to their constraints. Look at the graph that we have before. Here I've reproduced it in a smaller form. The blue line represents the budget constraint. That is all the possible combinations of toys and snacks that a consumer can buy with limited income given the prices. The red line represents the highest attainable indifference curve, the most satisfaction that our consumer can get. And here's that optimal point. What I've done is taken the graph we derived and put another graph beneath it. And this graph is our familiar price-quantity graph that we use for representing a demand curve. Notice, on the horizontal axis, I've represented the quantity of toys, just like on the axis above it. Quantity of toys is measured on the same scale on both of these axes. So a quantity that comes down to this axis can be dropped on down into the graph below it. These two graphs are measuring the same thing horizontally. Vertically, this graph down below measures the price of toys. So originally, our original price of toys, which was $3 per toy, I call that P0, the original price. At a price of $3 per toy, then our consumer wanted to buy 2 toys a week, say. So here's a point on the demand curve. At a price of $3 per toy, the consumer chooses to buy 2 toys a week. Now, let's change the consumer's constraints by lowering the price of toys from $3 per toy down to $1.50 per toy. When we do that, we have to redraw the budget constraint in the diagram above. So here I go. I'm going to redraw that budget constraint, and I'm going to draw it very thick and beautiful so you can see it on the web. There you go. There's the new budget constraint. Now, with this new budget constraint, we're going to be looking for a new indifference curve. And that's the indifference curve that's going to be the highest one we can get to given the constraint of the blue line. And as we saw before, in the case of Chris's preferences for toys and snacks, that combination is going to be at a point like this. Here's the new indifference curve, call it U1, the highest attainable one. And here, right here at this point of tangency, is the combination that Chris would choose to purchase in that situation. So when the price of toys drops from $3 a toy down to this new lower price of $1.50 per toy, when the price of toys falls, the quantity of toys that Chris consumes increases from 2 toys a week to, in our case, 4 toys. So let me take those 4 toys a week, and with a dotted line, I'm going to go down below the axis, down into my downstairs diagram. And here's my new quantity, Q1, of 4 toys a week. So let's put a new price quantity dot right there at $1.50 per toy and 4 toys a week, and there you have it. Hey, once you've got 2 points, you can connect them, right? And that gives you a demand curve. So you can imagine if we kept doing this exercise, we'd get an endless combination of price and quantity points, and that becomes the demand curve for toys for Chris. So I've labeled this curve D, that's demand. And this curve does all those things that you've seen demand curves do before. What's the purpose of this lesson? The purpose is to show you where a demand curve comes from. And where does it come from? It comes from consumers who have preferences and who have constraints imposed by prices and income, doing the best they can with what they've got. As their circumstances change, that is, as prices change, the optimal choice will change. And the demand curve is a record of those optimal choices. As the price rises and falls, the optimal point will move around upstairs in this graph. And as it does, we record it downstairs in this graph, the demand curve. The demand curve shows you what the consumer will purchase, the quantity of toys Chris will buy as the price of toys changes, holding constant everything else. Holding constant income, holding constant the price of snacks, holding constant Chris's tastes and preferences. That's where the demand curve comes from. And that's why we spent that time developing the indifference curve tool and putting it with the budget constraint and learning how to do consumer optimization. We're considering how to represent your choices in the world's coolest store. You have a limited amount of money to spend on toys and snacks, and you want to spend it so as to get the most satisfaction. Last time, we looked at this equation. This is the equation for the budget constraint. It tells you how many snacks you can afford to buy given your income, the price of snacks, the price of toys, and the number of toys that you choose. When we graphed this, we got the vertical intercept, which is the purchasing power of your income measured in snacks. that is, the total number of snacks you can afford to buy, given your income and prices. And we got the horizontal intercept, which is the total number of toys you can afford to buy. The slope of the budget constraint, which is this number right here, tells you the opportunity cost of an extra toy, measured in terms of the number of snacks you have to give up. What I want to do now is show you how this constraint changes when we change some of the things in the economic environment. In particular, what happens to your opportunities when your income changes or when the price of the products changes. Let's start with your income. What happens to your feasible set? What happens to your budget constraint, or the stuff you can buy, when your income is reduced? Let's suppose instead of having $12 worth of income, you only have $6 worth of income. In that case, how many snacks could you afford to buy? That's right, 6. And how many toys could you afford to buy? 6 divided by $3 per toy is only 2 toys. Now, the relative prices of toys and snacks are still the same. We haven't changed them, only your income. The way we show a change in income in this picture is the budget constraint will shift. In this case, it shifts inward because your purchasing power has shrunk. You now have a smaller set of toys and snacks that you can afford because of a reduction in your purchasing power. If your income should increase, the feasible set shifts outwards. That is, you can afford to buy more toys and more snacks. These intercept points, again, represent your purchasing power, what you can afford to buy, how well off you are measured in terms of toys or snacks. The slope of the line, however, again, still refers to the opportunity cost of toys measured in terms of snacks. Let's look at a second possibility. Suppose now, instead of changing your income, we change the price of toys. And let's cut the price of toys in half. Now, instead of costing $3 to buy the punching monkey, you can get the same punching monkey for only $1.50. And let's suppose the same is true for the vibrating sea mine and the squeaking nun. If all of our toys are now $1.50, how many toys can you buy with a budget of $12? The answer is you can afford to buy 8 toys. 8 times $1.50 equals your $12 income. Now, your purchasing power in terms of snacks has not changed. Snacks still cost $1 each, and you only have $12 to spend. So we show a change in the price of toys by rotating the budget constraint like this until we reach its new intercept. This is the budget constraint when toys cost $1.50 apiece, snacks cost $1 apiece, and you still have $12 to spend. A movement in the budget constraint, therefore, represents a change in your opportunities, a change in what you can buy, given your income and the price of the goods. If your income changes, then the budget constraint shifts outward for an increase in income and inward for a decrease in income. But the slope remains the same. As long as prices don't change, the slope remains the same. If we change the price, on the other hand, of one of the products, say toys, then we have to pivot the budget constraint. The budget constraint moves outwards in the direction of the product that's become less expensive. Now, instead of only being able to afford 4 toys on your $12 income, you can afford 8 toys, and that's why the horizontal intercept has moved out. Notice, because toys are less expensive now, you can afford to buy more stuff than before. The budget constraint has pivoted outwards. In the future, then, when you change the income, shift the budget constraint parallel. Keep the slope the same. But if you change the price of one of the goods, make sure that whichever good is becoming less expensive, that you're shifting the budget constraint outwards in that direction, in the same way that you would be shifting it inwards if one of the products became more expensive. This is how you manipulate the budget constraint to describe a change in the consumer's opportunities, a change in the feasible set of things they can afford.
Think fast. Which would you rather have? 4 toys and 3 snacks, or 6 toys and 2 snacks? Would you be willing to give up your animal crackers If it means that you could enjoy the dinosaur pistol and the bunny bowl, which would you rather have? 4 and 3 or 6 and 2? Maybe this is hard to figure out real quickly. Maybe it isn't. Maybe you'd just as soon have one as the other. We're now going to explore a tool that economists use to represent consumer preferences. This tool is called the Indifference Curve, and it becomes part of a map that represents all the combinations of goods that you find more, less, or equally desirable. Once we've drawn a map of indifference curves, we can put the indifference curves together with the budget constraint and derive the consumer's demand curve. That is, once we know what your constraints are and what your preferences are, we can use them together to predict your behavior. So let's get right to it. How do we draw an indifference curve? An indifference curve is defined as a set of points representing combinations of two goods, like toys and snacks, that a consumer finds equally desirable or equally satisfying. So we have to begin with a list that the consumer provides us that tells us those combinations that he or she finds equally desirable. Suppose we have a consumer named Chris, and we quiz Chris about toys and snacks, and he provides us with this list. This list tells us that Chris would just as soon have 2 toys and 6 snacks as 12 toys and 1 snack, or 4 toys and 3 snacks, or 6 toys and 2. All of the combinations represented on this table provide Chris with an equal amount of satisfaction. That is, Chris is indifferent among each of these alternatives. He'd just as soon have this one as this one or this one. Let's represent now Chris's preferences in a graph. Here we are back in goods space, and let's remember to label our axes. That's always important. The vertical axis is going to represent the number of snacks that Chris has, and the horizontal axis, just like before, is going to represent the number of toys that Chris has. Now let's take the information from the table and represent it in the picture. So we'll start with the combination of 2 toys and 6 snacks, and that will represent with this red dot right here. Next, we find the combination of 4 toys and 3 snacks equally satisfying, so we can put that point right here. Then 6 toys and 2 snacks gives us this point, and finally 12 toys and 1 snack gives us this point. All of these points represent combinations of snacks and toys. And all of these points, according to Chris's report, provide him with an equal amount of satisfaction. Now, you can imagine that there are a lot of other combinations in between these dots that represent combinations of toys and snacks that Chris finds just as satisfying. We can represent these infinite possibilities by connecting the dots and drawing a curved line that we call an indifference curve. So here I go, connecting the dots. And there's my indifference curve, a collection of points representing combinations of snacks and toys, all of which Chris finds equally satisfying. Looking at this indifference curve, you'll notice I drew it pretty carefully. I'm trying to make sure that the way I draw the indifference curve is consistent with what economists believe about people's preferences. Let me be specific. The first thing you'll notice about this indifference curve is that it's downward sloping. The downward sloping indifference curve means that both of these goods are desirable. That is, if we take away some of Chris's snacks, the only way that we can leave him just as happy as he was before is to give him some extra toys. Anytime we take away one of the goods, we have to compensate by increasing the quantity of the other. And that gives us a downward sloping indifference curve. Every time we lower snacks, we have to increase toys. It's another way of saying that more is better. If we had a combination of toys and snacks that represented an increase in both, well, Chris would prefer that, so it would have to be on another indifference curve with another set of combinations. For instance, suppose we consider a point like 2 for 6 snacks and 2 for 6 toys. Since that represents more toys and more snacks together than any of these points in here, that would be a point that would be way out here on another indifference curve somewhere. So a point that has more of both goods than a point on this curve would be more satisfying, and therefore it would lie on another curve somewhere, a curve that represents increased satisfaction. Another thing to notice is I've drawn this curve sagging downwards. We would call this a convex curve because it's bowed downwards towards the origin. A convex curve is a curve that has a decreasing slope as you move down it. Notice up here the slope is very steep. Then the slope gets a little flatter, and finally down here towards the bottom, the slope of the curve is very flat. Now you'll recall from our early math review that the way you find the slope of a curved line is to take the slope of a line that's tangent to the curve. So for instance, if we want to know the slope of this indifference curve at this particular point with 4 toys and 3 snacks, we would look for the straight line that is tangent to or touches the curve at that point. And that tangent line's slope is the slope of the indifference curve at that particular point. Notice that the slope of the tangent line as we move down the indifference curve is getting flatter. The slope is decreasing. The line is getting flatter as we move down the curve. Well, that's just a mathematical statement about what convexity means. But actually, this convexity has an economic interpretation. Notice that when you're way, way up here, whenever Chris has a lot of snacks and very few toys, the curve is steep. That means if we take away a lot of Chris's snacks, we only have to give him a few toys to compensate. Or to put it another way, if we take away one of his precious toys way up here, we have to get him a whole lot of snacks to leave him as happy as he was before. Just one toy less means a whole lot more snacks to leave him at the same level of satisfaction. Whereas if you're down at a point like this, and you take away one of his toys, you hardly have to give him any snacks at all to compensate. You can take away a toy with very little compensation because he has lots of toys. The slope of an indifference curve is called the marginal rate of substitution. And the marginal rate of substitution will be different as we move along the indifference curve. Up here, where the slope is steep, the marginal rate of substitution between snacks and toys is very large. If I take away one of your toys, I have to give you a lot of snacks to compensate. The marginal rate of substitution tells you how many snacks you would require in exchange for one toy. As we move down the curve, the marginal rate of substitution gets smaller and smaller and smaller. When we get way down here, where the curve is flat, the marginal rate of substitution is very small, which means if I take away one of your toys, that I don't have to give you very much snack at all to compensate you. That's because you've got a lot of toys. They're not as valuable to you in terms of snacks. So, a quick summary. The indifference curve slopes downward to represent the fact that both goods are desirable, and that you have to have more of one to compensate you for a loss of the other. Also, if you have more of both goods, you'll move up to a higher curve somewhere else, somewhere up here to the northeast. Finally, the slope of the indifference curve is called the marginal rate of substitution. And it's like a kind of internal price, a psychological price that you put on toys. If the marginal rate of substitution is big, then you want a lot of snacks to compensate you for the loss of a toy. Your price of toys in terms of snacks is high. But if you move down the curve and the marginal rate of substitution is small, then the price of toys for you in terms of snacks is small. That is, you're willing to give up a toy with very little compensation, with very little extra snack in return. This indifference curve, then, represents a set of combinations that Chris finds equally desirable. Well, let's look at another set of combinations that Chris finds equally desirable, but a set of combinations that provides him with more satisfaction than the combinations on this curve. Here's another table that represents a set of indifferent points for Chris. Chris would just as soon have 2 toys and 12 snacks as 4 toys and 6 snacks, 8 and 3, or 12 and 2. Now, all of these combinations are more desirable than the combinations on our original curve. How do you know that? You know that because right here we have a point that represents 12 toys and 1 snack. On this new list, we have the point 12 toys and 2 snacks. Since this involves more snacks and no fewer toys, that is, it's got more than the original bundle, it must be more satisfying because of our assumption more is better. Anytime you're moving to the northeast, directly to the north, directly to the east, or to the northeast in this diagram, you're moving to points that are strictly preferable, points and combinations that are strictly better. So let's go in and draw the picture that represents the combinations in this graph. Let's start with 2 toys and 12 snacks. That is, 2 toys and 12 snacks will take us up to this point. 4 toys and 6 snacks will take us to this point. And 8 toys, 2, 4, 6, 8 toys and 3 snacks will take us to this point. And finally, 12 toys and 2 snacks will take us to this point. Again, these are only a few of the combinations that provide Chris with this new higher level of satisfaction. If we connect these dots, we'll get a new indifference curve. Da, 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 da. Bam! All of these points are equally desirable. And all of these points are strictly more desirable than the points on the old indifference curve, since it's to the northeast, and more is better. Well, now that we've got a couple of indifference curves, we're going to need some labels to keep them straight. So let's call this original curve U0. U0 represents a number, and that number means the amount of satisfaction you get. We could call that utility. Utility is an economic term that means the amount of satisfaction that a consumer gets from consuming a bundle of goods. So U0 is the original level of utility or satisfaction, and we can label this new higher curve U1, which represents a higher level of satisfaction. Now notice I didn't put in numbers like 10 or 20 or 100 because, what would that mean? Numbers of utility. Measuring warm, fuzzy feelings in numbers. How do you do that? All I'm telling you is that however we measure satisfaction, the points on this curve represent a higher level of satisfaction than the points on this curve. One more thing to say about these indifference curves. Notice there are still points out there to connect with other bundles that are equally satisfying. I could spend all day drawing indifference curves, and these indifference curves would eventually fill up this graph. Indifference curves are everywhere dense. Every point on this graph has some other points that are equally satisfying, and I could spend all day drawing the lines connecting them. I would eventually have an indifference map, a complete representation of Chris's preferences. What can we say about this indifference map? We can say a couple of things. The first thing we can say is that the curves are everywhere dense. Everywhere you put your pencil in this graph, you are touching an indifference curve. The next thing we can say is that indifference curves can have all kinds of shapes. They don't have to be concentric circles. These indifference curves can be kind of weird blobby things as long as they're downward sloping and as long as the slope decreases as we move down the curve. One final thing, indifference curves can never, ever cross. Can you figure out why? I'll give you a hint. Remember, More is better. Let me show you. Suppose we had a situation up here where an indifference curve like this crossed over another indifference curve at a point like this. Now, how do we know that something like this can't happen? Well, we know from the following argument. Let's say we've got 3 points on this particular indifference curve, and we'll call them A, B, and C. Now let's take a couple of points that are on the other curve, and we'll call those points D and E. Now the thing that I want you to notice here is that point B is on both curves. That's what it means for the curve to cross. Well, according to this logic, D is northeast of A, that is, D has more stuff than A, so that must mean what? That's right, D is better than A. On the other hand, if you go down here, you'll see that since C is to the northeast of E, that must mean that this bundle, which has more stuff, is better. C is better than E. Well, if D is better than A, and C is better than E, we have a contradiction, because A is just as good as B, which is just as good as C. And if C is better than E, then A must, by transitivity, be better than E. However, we've already said that E is just as well liked as B, which is just as well liked as D. That's what it means for them to be on an indifference curve. Hold on. If A is better than E, and D is as good as E but better than A, then we've got a mess. We've got some kind of contradiction. How can A be better than E and worse than D, which is the same as E? It doesn't make any sense. It is illogical for these indifference curves to cross. You can't have more is better and have crossing indifference curves. So we'll put a big circle slash through this. This is not a possibility. Indifference curves never cross. Well, we've done a lot in this lecture. We've taken a set of preferences that Chris expressed, and we've represented them in a curve called an indifference curve, a collection of points that represent equally well-liked combinations of two goods. Then we saw that that indifference curve slopes downward, has a slope that represents a kind of psychological price called the marginal rate of substitution, and we saw that this indifference curve is part of a big indifference map that represents Chris's preferences for toys and snacks. Now, we're going to use this indifference curve along with the budget constraint to make some predictions about Chris's behavior, and eventually we'll be able to derive Chris's demand curve.
Recently, a neuroscientist reran the Pepsi challenge. In the Pepsi challenge, randomly chosen consumers tasted both Pepsi and Coke, and a majority of those consumers preferred Pepsi. In this rerun of the challenge, both blind taste tests and non-blind taste tests were performed. When the blind taste tests were performed, more than half preferred Pepsi. When the person drank his or her preferred drink, there was heightened activity in the ventral striatum. It's where the brain values rewards and benefits. In other words, their gut feeling led them to go towards Pepsi. When the subject knew which brand he or she was tasting, or it was a non-blind test, the brain used higher order cognition to make the choice. This came from the prefrontal cortex. When the typical subject knowingly tasted Coke and then Pepsi, the activity in the prefrontal cortex was stronger for Coke than for Pepsi, probably reflecting favorable images and feelings associated with Coke commercials. So the brand association developed from Coke advertisements dominated the gut feelings in favor of Pepsi, so more subjects went for the Coke. In other words, the branding affects brain activity and consumer preferences. What happens to a market when we set a maximum price? Well, sometimes we intervene in a market by controlling prices, and we can either set a maximum or a minimum. What types of goods do we set maximum prices on? Well, we know we have rent control, and gas prices are so high, people have thought maybe we should put a cap on gasoline prices, and the same is true for medical goods and services. So for all these goods, they've either have been subject to maximum prices or may be in the future. Well, let's look at the market to see what the effect of that would be. And so we can look at rent control, which is a classic example of having a maximum price. And in the market without rent control, we can look at a supply curve and a demand curve, where the equilibrium is going to be $400 per month per apartment, and there'll be 1,000 apartments rented at any one time. That's our market equilibrium. As you know, producer surplus is represented by the area above the supply curve but below the price. So it's this triangle right here. Consumer surplus is the area below the demand curve but above the price. So it's this area right here. So total surplus in the market is this triangle that goes from the price of 67 up to 900 over to point A and back to 67. All possible surplus generated in the market is either allocated to consumers or producers. Now suppose we set a maximum price and we rent control, and lowering the price from 400 down to 300. What would we expect to see? Well, at a rental of $300 per month, fewer apartments are supplied. The quantity supplied falls. So at point B, the price will be $300 and the quantity $700. And we can see consumer surplus has risen for all of those people that still have apartments because they pay a lower price. So consumer surplus is going to be this odd-shaped area that's colored blue. Producer surplus has been reduced. And it's been reduced both because fewer apartments are being supplied and a lower price is being paid. So producer surplus is this red triangle right here. Now we can also notice that the former total surplus, which was the entire triangle shown at equilibrium, is no longer the sum of consumer surplus and producer surplus. This yellow area here isn't producer surplus or consumer surplus. It's the decrease in total surplus when we've instituted a policy such as rent control. And we call that the deadweight loss associated with this policy. So the deadweight loss is the area of this little yellow triangle. Anytime we set a maximum price, we're going to create a deadweight loss. Who wins and who loses? Well, producers are going to lose because producer surplus unambiguously has fallen. Consumer surplus has changed. Those that still have apartments, their consumer surplus has risen because they pay less rent. But those that used to have apartments, the ones that were in the apartment 700 to 1,000, no longer have an apartment anymore, so their consumer surplus has fallen. Some consumers win, some lose, and producers' surplus has dropped. Overall, there's a deadweight loss created.
How does a tax cut affect prices? Well, we know that firms shift taxes forward to consumers in higher prices and backward to workers in lower wages. But what will happen if there's a tax cut? We would expect the opposite effects.
In 2003 in France, regular restaurants paid a very high tax on sit-down meals, while fast food restaurants paid a much lower tax on takeaway meals. The group of owners of large restaurants made a pledge. If the nation cut its taxes to the lower rate, it would cut prices to customers and it would increase wages to waiters and dishwashers. This is what one would expect when we look at what the impact of a tax is on prices.
Now let's answer the question, who really pays taxes? We're going to look at two phenomena called tax shifting forward and backward. So who really pays taxes? Let's look at a market for apartments. An initial supply curve, this dark red line, and the demand curve, this blue line.
At equilibrium point A, we have 900 apartments being rented at a price of $300 per apartment. Now let's institute a tax of $100 per apartment. That tax is going to shift the supply curve up $100 because the tax will increase costs associated with supplying apartments by $100. So we'll see a vertical shift up on the supply curve, and we can see if we compare point A to point C, that's a $100 shift. Now, who pays that $100? Well, at the new supply curve, we can see there's a new equilibrium at point B. At point B, there's only 750 apartments being supplied at a price of $360 per apartment. So we can see that the price has risen from $300 to $360. That means that consumers are going to be paying $60 more. And so $60 or 60% of that $100 tax will be paid by people renting apartments or consumers. While the price is $360, how much are apartment owners actually going to receive? They get $360 in rent, but they have to pay the $100 tax, so their net receipt is $260. So they're going to get $40 less than they did with the market equilibrium without the tax. And so consumers pay $60 of the tax, producers pay $40 of the tax. That's who pays the taxes. Taxes shifted forward to consumers and backward to producers. Now, who actually pays it? And the distribution of that tax depends on the slope of the demand curve. Let's look at two examples. Here we've got an inelastic demand curve. It's relatively steeply sloped. We can see that the price at equilibrium is $10. After a tax, in this example it's a $5 tax, creates a new supply curve. The price has risen to $14. So $4 of the $5 tax is paid by consumers in the form of a higher price when we have an inelastic or steep demand curve. The same experiment can be done on a relatively elastic or flat demand curve. Here we have the same shift of a supply curve up of $5. And we can see the price has risen from $10 up to only $1 because we have an elastic demand curve. So in this instance, with the elastic demand curve, only $1 of the $5 is going to be passed forward to consumers. The rest of it will be with producers. How does this affect surpluses when we look at a market when we institute a tax? Well, let's look at this market where we have thousands of pounds of fish per day and price per pound. And we'll look at an example with a perfectly elastic supply curve. Now suppose we have an equilibrium with the initial supply curve and demand curve at point A with 60,000 pounds of fish per day at a price of $2 per pound. And under that situation, the total surplus would all be consumer surplus. All the area underneath the demand curve and above the price, or the areas A plus B plus C, would be consumer surplus. Now let's add a tax of $1 to the market. That shifts the supply curve up by $1 and gets us a new equilibrium at point B. Consumer surplus is smaller. It's now the area A only, this blue triangle, the area under demand and above the new price. The area B represents the tax revenue that results from it. It's the $1 tax times the quantity that's being produced, which is 40,000 fish per day. So this rectangle, shaded red, is the tax revenue that's generated. And then area C is the deadweight loss that's associated with this tax. Now let's look at a different type of market intervention, controlling quantities. And we see this both when we require licensing for the production of a good or service and import restrictions. A good example of licensing is taxi medallions. In many cities, in order to be able to operate a taxi cab, you have to have a license or a taxi medallion. Now, let's look at the effect of this type of a policy. Suppose we look at the market for taxi cab services. and there's a supply and a demand curve. And at equilibrium at point A, there would be 10,000 miles of taxi services per day produced and consumed at a price of $3 per mile. And this would generate consumer surplus equal to this blue triangle and producer surplus equal to this red triangle. Now, suppose we think there are too many taxis and we reduce the supply of taxis by requiring licensing. In other words, we supply with 80 taxi medallions, which reduces the quantity to 8,000 miles of taxi services per day. And what will be the result of that? Well, if there was only 8,000 miles of taxi services produced per day, then the price would rise up to $3.60 per mile. And producer surplus, for those that get a license, would rise. So producer surplus is going to be this red shape, and anyone producing taxi cab services is going to have higher producer surplus than they did in equilibrium. Consumer surplus is going to be the blue triangle, which is lower because we're paying a higher price for a lower quantity. And we create a deadweight loss equal to this yellow triangle. Another example of controlling quantities are import restrictions. Let's look at a market where we might have import restrictions. This is a case where we have some foreign trade, so we want to differentiate between the domestic supply of a good or a service, and in this example we're looking at sugar, and the total supply for sugar, which is domestic plus foreign production of sugar. So we have domestic supply with a minimum supply price of 26 cents, and when you add in foreign supply also, or foreignly produced sugar, we have a supply curve that's farther to the right. As we see, the minimum supply price is going to be lower at 3 cents. Now, at this equilibrium at point A, we have 360 million pounds of sugar per day at a price of 12 cents per pound. And that's below the minimum supply price for domestic suppliers. So all the sugar is going to be produced by foreign producers, creating U.S. consumer surplus equal to this blue triangle, and foreign producer surplus equal to this red triangle. Suppose we decide that we want our sugar produced by domestic producers. So we ban the import of sugar. What that would mean would be there would be no foreign producers, and the only supply would be the domestic supply curve. If we only had a domestic supply curve, we would have a lower quantity of 160 million pounds of sugar per day at a higher price of 30 cents. What would happen to surpluses? Well, U.S. consumer surplus would shrink. Producer surplus for domestic producers would rise, but the foreign producer surplus would disappear. Let's try and get some more insights from neuroscience about consumer decisions. Remember, when we talk about neuroscience, we're looking at the gut feelings people have for both benefits and for costs, and then the cognitive ability to put those gut feelings together with other information. Now let's look at the choice between eating a donut and an apple. Both a donut and an apple give you a gut feeling of happiness, and both of them cost you money. And so we can compare the gut feelings of donuts and apples and look at the choice between the two goods. Additionally, there's other information we know about donuts and apples. Apples are a healthier thing to eat than donuts are. So when making this choice, we should combine all of those things, our gut feelings and the cognitive information that we have. Suppose we didn't. Suppose we just look at gut feelings. In this example here, we're looking at the consumption of donuts and apples. And this is the gut feeling marginal utility per dollar of eating donuts. And this is the gut feeling and cognitive marginal utility per dollar of eating apples. And remember, we're assuming that donuts are not as healthy as apples. And so there's going to be a difference when we include the cognitive decision-making process when we look at donuts. So first, let's take that part out. Let's just look at gut feeling for donuts. And if we use the equal marginal rule, we would consume at point A and point B, where the marginal utility per dollar is 12 for both donuts and for apples. Now suppose we include the fact that some people think donuts might be an unhealthy food. We include this cognitive portion of our decision-making process. That's going to lower the marginal utility per dollar of donuts under this light green line. If that's the case, then if we continue consuming 9 donuts and 1 apple, then our marginal utility per dollar will not be equalized anymore. The marginal utility per dollar of donuts is only going to be 2. So we have to shift away from eating donuts up to point E. We shift towards eating more apples down to point D, where the marginal utility per dollar is equalized at 7 across the 2 goods. So if we exclude the cognitive decision-making process from eating donuts, we would eat more donuts. The more we think about it, the fewer donuts we end up eating. We can also look at something called present bias, meaning should we spend now or should we spend later? And the spending later is savings. Spending now versus savings is a choice that we make. So we look at consumption now and savings and the marginal utility per dollar of each one. And we can look at the marginal utility per dollar of future spending or savings right now with present bias. So if we compare marginal utilities per dollars across these 2 different goods, consumption now or savings, we would get equal marginal rule, putting us at points A and point B, with $19 spent on current consumption and $1 saved, and 14 utils per dollar for each good. Now suppose we counteract the present bias and we understand that consumption in the future is a good thing. This would mean that the marginal utility per dollar would be higher for savings. Right? If that's the case, then we no longer have equal marginal between the 2 goods, current consumption and future consumption. If we stay at points A and B, or in other words, at 19 units of current consumption and 1 unit of savings, then we would have 38 utils per dollar for savings and only 14 utils per dollar for consumption. So we have to adjust away. We end up spending less on current consumption and saving more to points E and D, where our utils will be 26 utils per dollar across both goods. So if we can counteract our present bias, we tend to see less current spending and more savings. So people who are able to think into the future better tend to save more. How does present bias show up in everyday behavior? Well, let's look at credit cards. What do credit cards do? Credit cards allow you to get the current benefits right now, and the good feelings and the good gut feelings right now, and put the costs off to the future. So if you have a present bias, then you will spend more because you have credit cards. And this temporal mismatch between benefits and costs is made worse by the use of credit cards. What about smoking? Well, smoking, the act of smoking, has a mismatch of temporal costs and benefits. The benefits are right now. You have a good feeling from the nicotine. The cost of future health problems are in the future. So if you're a person that has a stronger present bias, then you're more likely to smoke than a person without a strong present bias. Now let's look at what the demand curve and the supply curve tell us so that we can analyze a market very carefully in looking at something we call consumer surplus and producer surplus. Remember what a demand curve looks like. Our demand curve tells us the relationship between price and quantity when we look at consumers. And the demand curve says that if you're willing to buy a certain quantity, what's the willingness that consumers have to pay for that last unit? So we can look at the willingness to pay of consumers by looking at the demand curve. Willingness to pay is the maximum amount a consumer is willing to pay for a product. So if you go up from the quantity and over, that'll tell you the maximum amount consumers are willing to pay for that last unit. If we look at a different quantity, the law of demand says that consumers are willing to pay more if we're talking about a lower quantity. So again, our demand curves tell us the willingness to pay, or the maximum amount that consumers are willing to pay for a given quantity. Now, consumer surplus is the amount a consumer is willing to pay for a product minus the price the consumer actually has to pay. And so we're going to actually see that consumers tend to benefit when they buy a good or a service, as long as they're willing to pay more than they actually have to pay. How does this work? Well, let's look at this demand curve. This demand curve shows us the number of lawns cut per hour. And so our market that we're looking at is lawn mowing. Right? And suppose the equilibrium price of lawn mowing is $10 per lawn. Right? If the price is $10 per lawn, and this demand curve represents different people's willingness to pay, we can look at lawn and see that for the first lawn that's cut, lawn's willing to pay the most. Lawn's willing to pay $22 to get that to happen. Thurl, on the other hand, is willing to pay $16. So Juan values having his lawn cut more than Thurl does. And then Forrest, $13. And if we look at Siggy, Siggy's only willing to pay $7. So if the market price is $10, well then that's more than Siggy's willingness to pay. It's less than Juan's willingness to pay, less than Thurl's, less than Forrest's, less than Tupac's. And it's exactly equal to how much Favola is willing to pay. So if we look at consumer surplus, which we are going to define as the difference between the price that's paid and a consumer's willingness to pay, we can look at Juan. We know that Juan is willing to pay $22, but the price is only $10. So Juan is benefiting by the difference, or $12, between his willingness to pay and the price he actually pays. So this distance between the demand curve and the price is Juan's consumer surplus. We look at Thurl. Thurl's willing to pay $16, but only has to pay $10, so he's benefiting by $6. If we look at Favola, Favola is exactly equal. Willingness to pay and price of $10, so no consumer surplus is generated. Ultimately, we look at this consumer surplus generated in a market as the area underneath the demand curve, but above the price. So it's the area of this triangle right here. Now we can also look at producer surplus. So remember, our supply curve shows us the relationship between price and quantity for suppliers. And if we look at any given quantity, we can go up to the supply curve and over, and that's the minimum amount a producer is willing to accept to produce that unit of the good. So when we're looking at supply curves, we can look at what's called producer surplus, where producer surplus is the price a producer receives minus the marginal cost of production, because the marginal cost of production determines the willingness to accept, the minimum price that a producer is going to require to produce that unit of output. How do we show that on a supply curve? Well, in the same way we looked at the lawn mowing industry and the price per lawns and the quantities per lawns, and we were looking at the demand curve, we can do the same along the supply curve. So here's the supply curve, and these are the willingness to accept for different producers. So Abe is willing to mow a lawn for $2, B is willing to mow a lawn for $4, and Cecil's willing to mow a lawn for $6. Efren, on the other hand, requires $12. So now suppose the price in the market again is $10. What do we see? Well, we see Eve is breaking even. Eve's willing to mow a lawn at a price of $10 and is getting $10. But Abe is willing to do it for $2. So Abe is collecting a producer surplus of 10 minus 2, or $8, the distance between the supply curve and the price. Cecil is getting $4, 10 minus 6. and D is getting $2 of producer surplus, 10 minus 8. So when we look at producer surplus, it's the area of the triangle underneath the price, but above the supply curve. So it's this triangle right here. We want to get very good at looking at producer surplus and consumer surplus, because when we start looking at interventions in the market, we want to see what happens to producers, what happens to consumers, and if we still get the same outcomes as far as surplus that's generated.